Okay, so let's officially start. Hello, everyone. Welcome to episode 34 of Warsaw Quantum Computing Group Meetup. Today we have a special guest from XANADU, Antal Szava, and the title of this talk is Using PennyLane for Quantum Differentiable Programming. Before we start, we would like to thank our strategic partners for supporting us, Snarto and COGIC, and I would also like to thank our honorary partners for helping us in advertising this event. Yeah, I think that now I can stop sharing my slides. And Antal, if you are ready, the Zoom is yours. You can start sharing your slides.
So I think you should be seeing my screen now and hearing me as well.
Yes, awesome. I can see your screen. So maybe just a quick message to our participants before we start, because I've already told you at the beginning that if you have any questions, please post. So you can post your questions on our chat, and there will be, of course, a Q&A session at the end. But we also agreed with Antal that this lecture can be interactive. So if you have any questions related to what Antal is saying, feel free to interrupt and also ask your question. You can then unmute yourself. But beside questions, please try to keep to stay muted. Yeah. So now I think that we can start the main lecture. So Antal, the Zoom is yours.
Sure thing. Thank you so much. So welcome everyone. My name is Antal Szava. I'm a quantum software developer at XANADU, based in Toronto. I'm also the leader for the PennyLane core subteam that is working on the PennyLane software library. So today's talk is titled Using PennyLane for Quantum Differentiable Programming. I would just like to get a little bit, give a little bit of introduction to what quantum differentiable programming is and how you can use PennyLane for this. Just before diving into it, I would just also like to thank the organizers and Pavel Gora in specific for inviting me and for the interest and curiosity in both PennyLane and XANADU. So without further ado, let's just dive right into it. So what really is PennyLane? We have a small summary of what PennyLane is. It's an open source Python library for differentiable quantum programming of near-term devices. The idea here is that you can access the entire source code of PennyLane just by browsing through GitHub and the repository on GitHub there. So if you are keen to see how we achieve certain implementations of quantum computing capabilities, you can just go there and see what we have come up with. It is mainly a library for differentiable quantum programming, and we will very much elaborate on the differentiability and the quantum programming aspect as well in a couple of minutes. PennyLane is tailored towards using near-term devices. We are still in a noisy intermediate scale era when it comes to quantum devices. Therefore, it is very much important to see how we can use such devices that are not yet tolerant to faults. PennyLane is much tailored towards using such devices. Now, let's elaborate a little bit more on what differentiable quantum computing and quantum programming is in depth. Differentiable programming is basically the idea of writing functions in your programs and writing the gradients of such functions as well, alongside with the functions that you have written. Once you provide gradient functions to each of the functions that you have written, you can then make your entire program end-to-end differentiable. This is a key thing that you can just use when you would like to get gradients of entire programs. There are multiple software libraries such as TensorFlow, PyTorch, or JAX that allow you differentiable programming capabilities. On the other hand, of differentiable quantum programming is the quantum computational capabilities that have been developed throughout the 20th century and are being developed very actively nowadays as well. The idea here is that we can harness quantum mechanics in order to perform certain quantum computational solutions when we are tackling certain issues. Now, let's have a look at the right-hand side of this slide. Here we have a small quantum circuit, which consists of three main parts. First off, we have three quantum bits or qubits, and we initialize each of these qubits in the 0 state. When referred to this initial state, what we can say is that this state will be a ket psi state. This is using the bracket notation that is very much popular in the quantum computational community. Once you have initialized your states for each of the qubits, we can then evolve this state vector that we have by a certain unitary transformation u. One thing here to note is that we will be parameterizing this unitary transformation u by some theta parameters. This unitary transformation will then summarize these rotation gates that we have on each of the qubits along the y-axis. So what we can say is that if we have a y rotation gate on each of the qubits, we will just basically conclude and substitute this entire interaction by a unitary transformation u. Just a note, as we are going through, I might not see any questions that arise, so please feel free to unmute yourself if you have any questions as we are going through these slides. All right, so
there are no questions on our chat, so we can continue.
Sounds good. Okay, just feel free to interrupt me. All right, so this was the second step that we have in a quantum circuit, having the unitary transformation. At the end of the quantum circuit, we have certain quantum measurements, and these quantum measurements are used to get quantities related to certain observables. Usually these are physical Hamiltonians that we can encode.
Yeah, is there any question, Virat? Would you like to ask something? Okay, maybe it was just an accident. All right, please go on, Antal.
Sounds good. Okay. So this is just the basic idea behind quantum circuits. Using quantum circuits can be great to then define certain expectation values, quantities that can be used to get very interesting physical quantities in practice as well. So getting the expectation value of a certain quantum observable can follow from something that is referred to as the Born rule from quantum computation. And it really is summarized by this formula here. On the right-hand side, what we see going from the right to the left is the state vector, that is the ket psi that we have seen previously. This is going to be the all zero state in our quantum circuit from the previous example. This is then acted on by some sort of a unitary transformation parameterized by a theta vector of parameters. Then we have the observable itself that acts on the evoked state vector. And the left two terms are going to be the adjoints of the unitary transformation, as well as the ket state vector, giving us a bra psi here. The key takeaway to see here is that this entire expression can be computed just by using matrix-matrix multiplications when representing the unitary transformation as well as the observable by some sort of a matrix. And we can also just use matrix vector multiplications when multiplying the state vector with the unitary transformation itself. So the reason why this is very important is that we can use frameworks such as TensorFlow or PyTorch in order to compute such expectation values, since these software libraries allow us to operate with tensor-like objects. Once we have a look at how differentiable programming and quantum circuits could be used hand in hand, we can just follow and go to the idea of quantum differentiable programming. The idea here is that we could define a certain f function that takes an input feature vector x that is going to be classical data that are non-trainable, as well as a trainable vector of gate parameters theta And these theta trainable parameters can then parameterize the unitary transformation that we have inside of our quantum circuit. Once we have such an f function, we can evaluate this function f and get results from our quantum circuit computations. The idea behind this is going to be that we could potentially train these theta parameters in order to train the quantum circuit and quantum computers themselves. Let's have a look at how we can use these quantum circuits to be trained, not just in smaller quantum circuit evaluations, but also in bigger hybrid classical networks. The idea is we can get special quantum circuits, referred to as variational circuits, and use these variational circuits with trainable classical models in order to then create bigger hybrid models. Now, I introduce this variational circuit. We will see what quantum variational circuits are in just a second. But the key takeaway here is going to be that you can create hybrid models where you have quantum nodes as well as classical nodes. And it is very much worth noting that such quantum nodes can be executed on separate quantum hardware as well. So here we have two distinct quantum nodes. It can be that, for example, this is computed on a hardware provided by IonQ, for example, but this other quantum node can be, for example, computed or executed on a hardware provided by XANADU. The key thing here, what we have then is an end-to-end hybrid network that we can differentiate over from the input towards the output. Now you might ask yourself, okay, we are using TensorFlow or we are using PyTorch. How can we actually input PyTorch tensors into quantum devices? Do they understand these tensor-like objects? The answer is no. What we can do is to unwrap the numerical information from these tensor-like objects, input these numerical information into the quantum device, evaluate the quantum device or obtain its gradient. We will have a look at how we can obtain quantum gradients in just a minute. And once we have such results, we can just convert them back into the tensor-like objects that we are using from a specific machine learning framework. All right, so we've seen how we can use hybrid models and how we can have quantum as well as classical nodes in our hybrid models. We have also seen how we can use machine learning frameworks in order to differentiate over the entire model. Now, you might ask, okay, this is really great, but can we actually use these quantum computers to solve meaningful problems? And the answer is maybe yes and no at the same time. There are certain things we can already do with the quantum hardware available there, but all in all, most of the hardware that is there is still noisy. The software capabilities are being worked on as we speak, and there is also a vast theoretical foundation that is being laid just as we know it in the coming years as well. I also mentioned that there are also things that we can do right away already, and this idea really connects to something that is called this noisy intermediate scale quantum computational era that we have at the moment. And this is something where we go back to these variational circuits that we have already mentioned previously. Now, the key thing here is that we can create variational quantum algorithms in order to tackle certain issues. The first step here is to take a quantum circuit that we kind of know is going to work. That's why it's called a circuit ansatz. It's kind of an educated guess of a quantum circuit. Once you take such a quantum circuit, you can then encode certain quantities such as Hamiltonians into the measurement of such quantum circuits. And once you get expectation values of observables, so for example, you get the expectation value of a target Hamiltonian, you can then use such expectation values to create problem-specific cost functions. Examples here, very popular examples, include the variation quantum eigensolver to get the ground state energy of certain molecules, for example, but it also includes solving graph-based problems using the quantum approximate optimization algorithm. Once you have your cost functions defined, you can just take another step forward and define your training procedure. Once you evaluate your cost function, you get some sort of a result, but this might be very much off from the analytic value that you are curious about. So what you can then do is get the gradient of your entire model, and you can try to just train and update your trainable parameters, input it into the quantum circuit as well as your cost function. By doing this procedure, you can then move towards the analytical values that you are curious about step by step. Now here is a very key insight that I would like us to have a look at. We've said that quantum computers could potentially be used for training procedures, and we are also comparing them to classical neural networks and how they could be used as part of a hybrid models, right? The main thing here with quantum computation is that we have the promise that for selected problems, quantum computation could surpass classical simulation capabilities, right? That would be one of the promises. How could we then get the gradients of quantum circuits just by using classical computation? How could we train quantum computers if just simulating quantum circuits can be intractable classically? Well, the answer to this is given by some family of rules that are referred to as the parameter shift rules. The idea here is that if you have a quantum circuit and you represent it with some sort of a function f that takes a vector of thetas as input parameters, and you would evaluate this function at the position theta. If you instead evaluate the function at two other positions, theta minus s and theta plus s, then using these results, you can actually recreate the gradient of function f at position theta. Now, just elaborating on this idea, what we are doing here is that we are shifting the theta parameters into the negative direction with some shift s, and into the positive direction with some shift s, doing arithmetics, and at the end, multiplying the result that we get with a certain constant value. Going further and trying to understand the parameter shift rule, we can draw similarities with trigonometric functions, such as the sine function. So let's say that we choose the sine function as a target function, and we would like to provide its gradient. Well, its gradient is going to be the cosine function, but there's also a trick that we can use here. We can express the cosine function by evaluating the sine function at two different positions. So if we evaluate the sine function at theta plus pi over 4, and we evaluate it at theta minus pi over 4 as well, we gather the results, do arithmetics, and multiply it by 1 over the square root of 2. What we then do is we effectively compute the gradient of the sine function by using the sine function itself. One key thing to note here is that while the parameter shift rule is analytic in nature, it is not the same as something that is referred to as the finite differences rule. The finite differences rule is an approximation method that can be used to get close enough values at times for quantum gradients. But the key thing here is that the parameter shift rule will be using these shift values that are relatively big in nature, whereas the finite differences rule will use shift values that are very much small in magnitudes. The parameter shift rule will provide the exact analytic values, whereas the finite differences rule will only provide an approximate value to the gradient. It is also worth noting that with the finite differences rule, you may be experiencing numerical instabilities, especially when using noisy devices. All right, so we've seen that the parameter shift rule can be potentially used to get the gradient of quantum circuits. This will actually help us out when we would like to define our training procedures. Because what we've seen, for example, in machine learning and in differentiable programming as well, once we can provide the gradient of our programs, we can just differentiate over the entire program and potentially train it with a procedure that we are defining, usually using gradient descent optimization methods. All right, this was a minor introduction to quantum differentiable programming and the ideas behind. Next, I would like to just step further and go for what we have in PennyLane and how you could potentially use PennyLane. I might just take a second again and see if there are any questions here, but feel free to interrupt me, but I see none, so I might just proceed.
Yeah, we can proceed. Mm-hmm.
Okay. Okay, cool. All right. So let's get into what we are doing with PennyLane and what we are offering here. So first off, let's have a look at a small example using PennyLane. Let's have a single qubit that is initialized in the 0 state. And we have two rotation gates that then act on this 0 state. We have an X rotation gate and we have a Y rotation gate as well. At the end of the circuit, we will then be applying a quantum measurement that is going to be in the Z basis. Now, this entire simulation can also be just represented by the block sphere itself. This block sphere is a handy tool that helps you see how a qubit can be just interacted with itself. So, for example, here what you have is a state vector that is in the 0 state, and there are two axes. So you have the two axes that we will be using with the rotation gates. So you have the X axis and the Y axis, and our goal would be to get this single qubit from the 0 state into the 1 state. Now, using PennyLane, we can very much just define this problem, and we can just solve it by running the quantum circuit on a device. So for this, first we just import PennyLane. We also import PyTorch. We will see later why we will be using PyTorch. And we will also be using a plugin that is the AWS Bracket plugin to interact with PennyLane. Now, in order to use this plugin, we also just define our AWS S3 bucket just to store information about our simulation. And this example will show how we can potentially use a real quantum computing device serviced by Rigetti. Once we have these initial details set up, we will then define the PennyLane device by using the QML.device top-level function. This device will have 32 qubits, and this will just be useful for us to run our simulations. Once we have our quantum processing unit set up, we can then define our quantum node. So here is where we will be using the QML.QNode decorator to create a quantum node. We will be using the device that we have just defined, and we will also be interacting with the PyTorch interface that we have. The key idea behind interfacing with PyTorch is that the quantum circuit that takes two parameters can now interpret PyTorch tensors as well. So the circuit is going to be just the circuit that we have had a look at. There's going to be an X rotation gate for acting on the qubit that we have, a Y rotation gate acting on the same qubit, and we will also be gathering the expectation value of the poly-Z operator on this single qubit. Now, one key thing here is that in PennyLane, we call qubits as wires. So we have our device, we have our quantum node set up. At this point, we can set up the classical optimization method that we would like to use. And for this, we now define a cost function that will use the expectation value gathered from the quantum circuit. And it will just be used, this expectation value just be used to provide a quantity that can then be minimized in order to effectively move that single qubit from the 0 state into the 1 state. Before kicking off the optimization, we just provide certain initial values. These values can be arbitrarily chosen. We choose an optimization method. We provide the steps for the optimization, and then we optimize over our procedure just by calling the cost function. So this would actually have to be a cost here instead of the circuit. And we optimize over this function step by step in order to then train our network. This previous example was great because we've seen that PennyLane can be interfaced with machine learning frameworks. PennyLane is framework and hardware agnostic. So we've seen an example where you could interface with the quantum differentiable frameworks just by having machine learning frameworks as well as quantum software libraries such as AWS Bracket being used with PennyLane. Well, the idea here is that you can have simulators and hardware devices from other quantum software libraries, but you can also use some machine learning frameworks such as TensorFlow, PyTorch, AutoGrad, or JAX. So this is very great because it might be that you are new to PennyLane, but you have used other quantum software libraries. So you can just have a look at what type of plugins we have, and you can use devices, for example, from other quantum software libraries. So previously we've seen how hybrid networks can be trained. Using PennyLane is great because you can actually do this training because one of the focus that we have in PennyLane is to provide end-to-end differentiability. So we put quite an emphasis on differentiability, and we do this because we can provide differentiability both on hardware and on simulators as well. On hardware, we've seen the parameter shift rule, which works great. On simulators, you can use other techniques related to automatic differentiation and backpropagation. Going a little bit more in depth into how you can get gradients, what you do in PennyLane is define this diff method argument when defining a quantum node. You define this, this differentiation method. For example, when using a hardware device, you can just set it to the parameter shift rule. This will, in effect, get the gradient of a quantum circuit by evaluating the quantum circuit multiple times. If you are using a simulator device, you have multiple approaches that you can choose from. You can use the backpropagation method to, when you are using a simulator that supports backpropagation with certain machine learning frameworks. You can also just use the adjoint differentiation method that is very, very much fast, and it also provides a memory efficient way when using certain simulators that have the support for it. If you are okay with not getting analytic results, you can also just get you can just use the numerical finite differences rule that we have already mentioned when compared with the parameter shift rule. We provide a wide-ranging built-in group of simulators in PennyLane. One of them, which is usually the most used, is the default.qubit simulator. This is a qubit-based pure state simulator that also supports backpropagation with PyTorch, TensorFlow, JAX, and AutoGrad as well. We have another device called default.gaussian that is helpful when simulating certain continuous variable-based devices. It's basically a device for continuous variable-based simulations. It is mostly minimalistic, so its capabilities range for basic continuous variable quantum circuits. If you would like to simulate more complex CV-based circuits, you can just check out, for example, the Strawberry Fields software library that we provide from XANADU. If you would like to simulate qubit-based systems and also add noise to your simulations, what you can do is to use the default.mixed simulator. This is a great way of simulating hardware and trying to get more and more close to the real hardware simulations that we have in place. The last device that I would like to mention here is the Lightning.qubit device. This is a device we've been working on for some time now, and it is now shipped by default with PennyLane, with the 0.18 release that we have made. On the right-hand side, you can see a comparison between default.qubit and lightning.qubit for the adjoint differentiation method, and it's much faster to be used for most use cases. So I really recommend you that you check out lightning.qubit here. We've previously seen that we have certain plugins for quantum software libraries. If you are familiar with, for example, Qiskit or PyQuil, and you would like to start picking up PennyLane, what you can do is define your quantum circuits in the framework that you are familiar with. So in this example, you can just define it in Qiskit, and you can use top-level functions from PennyLane to load your quantum circuits into the quantum circuits that you are defining in PennyLane. So in this specific example, you could use the from Qiskit top-level function to define quantum circuits in PennyLane. We've also seen that variational quantum algorithms are very much to be used in this era that we are in. There are lots of embeddings, layers, as well as state preparations that repeat themselves throughout the literature itself as well. So we have a growing base of such templates that you can use as plug and play in your quantum circuits. These are basically recipes for Ansätze as well as for quantum circuit building blocks. So in this very example, you could, for example, use an angle embedding to embed your classical information, followed by some sort of strongly unlengthening layers. The idea here would be to allow some sort of layers to train your quantum circuit. Next to the basic capabilities that we offer in PennyLane, we also have a quantum chemistry subpackage that can be installed using pip. This quantum chemistry subpackage is great to convert between electronic molecular structures to PennyLane observables. Now, this subpackage uses other packages such as Psi4 and PySCF, and we have also seen that this is at times a limiting factor. So, for example, some quantum chemistry packages are not supported on Windows. So there will be something else I will mention very shortly, where we've worked on a small module that can be used to simulate Hartree-Fock simulations using PennyLane itself only, and not any of these extra libraries. So I've really given just a small introduction to what PennyLane can be used for, but there are many more examples and applications online that we have. I really encourage everyone to just check out the PennyLane.ai website here. We have a growing number of demonstrations that you can have a look at. Before closing, there are just a couple of things I would like to further share. And these things are very much what we are excited about at the moment. So in PennyLane, we have a very new circuit drawer, which is very much a great addition. What you can do is to define your quantum node, then use this qml.drawMPL function, and you can use it to draw quantum circuits using the matplotlib framework. Another thing that is very much new related to quantum chemistry is what I've previously mentioned, which is a differentiable Hartree-Fock solver. The idea here is that you can differentiate over not just the circuit parameters that you have, but also the molecular structure of your problem. And you can also just, excuse me, you can also just get the gradient of basis state parameters, for example. Apart from the features that we are developing, we also have a great event coming up in February that is called QHack. So in the middle of February, we will start a nice event where there will be quantum computing questions distributed to participants. I encourage everyone to check out QHack and sign up if you're interested. We will have also a wide variety of talks being given throughout this event. If you are keen to learn more about quantum computation in general, and you would like to do that by learning with PennyLane, the XANADU Quantum Codebook is a great start there. This has been a curated set of questions that you can solve through and just go through while using PennyLane and learning more about quantum computing. With that, I would like to just thank you for your attention and just open up the floor for any and all questions that you may have.
Great, fantastic. Thank you very much, Antal. It was very interesting and very informative. In fact, there are several questions. So let's start from the end this time. So there's so maybe the question number 0. Is it already possible to sign up for the QHack hackathon? Is the registration okay? Mm-hmm.
Yes, signups are available. So let me just go back. If you go to qhack.ai, you will actually have this sign up button there just available. So this is an exact print screen basically of the website that you will see, and you can just see what type of rewards you will be eligible for if you sign up and solve the questions in a great fashion.
Perfect. There are 2 more questions about QHack. So the first is, will QHack be strongly music related hackathon this time? I guess that I'm not sure what was the exact reason, but indeed we can see some let's see, musical motifs here.
Yeah, yeah, that's a great question. I think the theme itself is music related. Many of the names that we have at XANADU are related to music, as well as many of them are related to, for example, Beatles songs.
Yes.
Last year we had a talk related to quantum music, so basically music produced by quantum computers. Truth be told, I'm not sure if we will have a similar talk this year, but it might very much, yeah, it might be.
Great, fantastic. Is the QHack individual participation or in teams?
Yes, that's also a good question. Last year it was a team-based one. I would think that we have the same this year, but the team-based sessions were mostly related to the second week of QHack. First, solving the questions themselves were individual in nature. So we had a set of questions that you could just solve, and you could then put yourself on a leaderboard where you can gain more and more points as you go through the questions that you are solving. So in that regard, it's kind of a mixture of both.
Okay, great. So now coming back to your talk, to your lecture, there's a question from Adam. What if the same angle is used several times in ansatz? Is it possible to consider such circuits?
Yes. So I would assume same. Definitely, I would think that just an answer to this question would be you would then regard these same angles as you could potentially regard it as different trainable parameters, but if you want, you could potentially regard them as the same trainable parameter. I'm not quite sure which one was meant here.
Okay. Adam, would you like to clarify? Maybe if so, you can unmute yourself and ask. But if not, then that's
Hello, do you hear me?
Yes, we can hear you.
Okay, the main motivation for me was just QA whether because if you have if you use angle several times in the circuit, then you have to slightly update the parameter shift rule, and you have to my best knowledge, you have to apply it several times and get the linear combination of the results. And so was just curious whether PennyLane can do it automatically. Somehow it guesses or just observes that the same theta was used several times.
Yeah. So what PennyLane would do in general is it would have a classical layer kind of, so there would be a classical pre-processing. So even if you use the same parameter multiple times, it would then regard those parameters as individual trainable parameters.
Thank you.
All right. So now we have a series of some general questions about PennyLane. So the first, so PennyLane is an open source project supported by XANADU. So that's the first question. So is PennyLane an open source project supported by XANADU? The second question is, could PennyLane be used for applying meta-heuristic optimization algorithms? By meta-heuristic optimization, we mean, for example, genetic algorithms, particle swarm optimization, and so on.
Yeah. So for the first question, it is an open source project. There is basically the entire project is open source by XANADU. It is kind of a subset of what XANADU is doing. So XANADU is a kind of a hardware company, first where chips and quantum devices are being produced for continuous variable quantum computation using photonics. PennyLane is a software library that we are also working on at XANADU. And yeah, just going back to the original question, it is completely open source. The second question related to heuristics and I believe it was evolutionary algorithms, perhaps.
Yes.
Yes. We don't really have any specific templates tailored towards those goals, but I would think that I'm not aware of any hindrances as to coding such things up.
Okay. All right. Fair enough. There are some other questions. Question from, let's go back. Oh, okay. I'll ask a question from Pavel. What's the biggest molecule you can simulate in PennyLane right now? Or maybe that is restricted to quantum hardware that you use?
Yes, that's a great question, actually. I would think it's restricted on if used on quantum hardware, indeed on the quantum hardware itself, or even if we are using simulators, we would be restricted on the simulator itself. So things would come in to play, such as how we are using the state vectors and how we are using the memory in our classical devices, because usually we would have to create the state vector, and if we are using a pure state vector simulator, that's going to be different to when we are also simulating noise, for example. To give a ballpark number, I would think on a laptop that you are using, you could potentially go up to 20 qubits usually, but it also comes down to the memory that you have. And for better workhorse machines, you will get to simulate bigger molecules.
All right.
One other thing to clarify here is that
yes, let's go on.
Yeah, it's just really I wouldn't say it's really specific to PennyLane. It's more so specific to quantum computation and how we can simulate quantum circuits.
Okay, great. There's another question from Achari. What differentiation tool are you using in PennyLane? Do you use JAX framework? I think that it has been already answered, but you can explain once again.
Yes, that's a great question. So indeed, we have interfaces for TensorFlow, PyTorch, including JAX as well, and AutoGrad. So we have these 4 interfaces at the moment, and the default.qubit device provides backpropagation capabilities for all of these interfaces.
Okay, good. There's one more question from Achari, this time related to QHack, I guess. Will it be restricted on using PennyLane language only?
I believe the main language will be PennyLane. Potentially, you could use certain plugins, for example, that are available. But for example, answering the questions that we will have will very much likely happen in PennyLane.
Okay, good. Do we have any more questions? So at the beginning, you mentioned that the method that you present might be particularly useful in the near term, as you said. But how do you think, what may happen after the NISQ area? So it's quite far from now, but do you think that similar methods might be applied then, or we'll just come up with some better approaches that can just outperform the approaches that you presented?
Yes, it's a great question. Truth be told, I'm not really sure. I believe that we will still remain in the NISQ era for some years now. And there are, of course, algorithms such as Shor's algorithm or Grover's algorithm that are kind of the light at the end of the tunnel, so to say. We are trying to go forward towards those algorithms to be used. But yeah, I wouldn't be able to make any better guesses.
Okay, yeah, that's fine, fair enough. All right, so just out of curiosity, why do you decided to call qubits as wires, right? Do I remember correctly? It was wires, I guess, right?
Yes, yes. The reason here is that as shown with the devices as well, we have devices that are tailored towards qubit-based, towards the qubit-based model, but we also have continuous variable devices. Built in, we have the defaulted Gaussian device, but with the PennyLane SF plugin, we also have other continuous variable-based devices. So the idea there was to have some sort of a name that we can use both for qubits as well as for quantum modes or Q modes that are usually used with the continuous variable systems.
Okay, yeah, that's good. Do we have any more questions to Antal? I think that we've already asked all the questions that we had on our chat. All right. So yeah, maybe there will be some more questions later. In such a case, we'll try to reach you out. But anyway, Antal, thank you very much. It was a fantastic presentation, and also the discussion was very interesting. There were many questions, so I believe that our participants also enjoyed your talk. Let me maybe just share my screen for the last time today, so we'll be finishing.
Can I ask you the question, please?
Yes, go on.
Okay. My question is XANADU have offices in Europe or just in Canada, are there any open positions in Europe with XANADU?
Yes. Hi, Akari. So at the moment, we only have an office in Toronto. There are open positions posted in the XANADU.ai website. So the main idea would be to relocate to Toronto with most of the positions that we have open. But I would just encourage you that if you are interested in applying for any of the positions, maybe reach out and also potentially just include if working from Europe could be an option there.
Okay, thank you.
Yeah. So Antal, how do you think, would it be possible to work remotely from Europe as well? How did you work during the pandemic crisis, for example? So
I would say that we are working mostly from Toronto, you know, but there are of course, especially now in this situation, cases where we might be working remote. I mean, we are working mostly remotely, and it might be that we are not all in Toronto, located in Toronto all the time. Okay. So that's why I would say the main thing is working from Toronto, but it might be worth just asking. And honestly, I cannot promise anything, but it's worth a question.
Okay. All right. Good. Do we have any more questions to Antal before we finish? So if not, then just to wrap up, I would like to thank once again our strategic partners for supporting us, our honorary partners as well for helping us in advertising our events. And I would like to invite you to attend our next meetup. It will be in February. Katarzyna Rycerz will give a talk. It will be 14th of February, so the same day on which the QHack will start. So don't forget to sign up. I hope that Antal encouraged you enough to just sign up and try. So there's still more than 1 month to start. So yeah, we hope that we'll meet again, maybe even with even more people next time. So Antal, thank you once again. It was a pleasure to have you with us, and thanks to all the participants. I will send you, so first of all, I will send you the survey to ask about your opinion and how we can improve. And we are going to prepare a video recording. It should be available on our YouTube channel within a couple of days. So also stay tuned. And with this, I would like to finish. So I'm stopping sharing my slides. Any last thoughts for today? So there are some congratulations and the words of thanks and acknowledgements on our chat that it was a great presentation. And all the best with developing PennyLane. So I think that everyone agrees. So yeah, thank you once again. Have a good day or evening wherever you are, and have a happy 2022 year. We're looking forward to meeting you again.